Okay, thank you very much. It's very exciting to be with you today, and I'm surprised, how interesting law can be, and computer science too. So I'm an economist, and I find this whole thing very fascinating. For me, a blockchain protocol, I think of it as the rules of a game that players will participate in. And the players are maybe the miners, maybe the developers. And economics has a very nice disciplined way to approach interaction of players within a game. It's called game theory. And so what game theory emphasizes is that people will make the actions that they believe are the best for them, but they are interacting with the others. So when they do that, they need to think, or what are the others going to do? And so my beliefs about what the others are going to do is going to have an influence on what I do. And this, I think, plays an important role in the blockchain. For example, in the blockchain, I think there are important coordination problems. And let me give you an example that is not directly related to the blockchain, but just to give you an idea of what I mean by coordination problems. So yesterday night, I had to think what I'm going to wear today. So my own preference would have been to come with a short and a T-shirt because it's very hot. But I'm thinking, OK, if I go there and I'm wearing a short and a T-shirt and I'm the only one, maybe it's not going to be OK. So now, I was kind of safe and anticipating no one would be wearing a suit and a tie, but in some contexts that could happen. And so I basically thought, okay, people are going to be like, in between, casual chic, and so that's what I tried. So the idea is, I had to form beliefs about your behavior to find out what was my own best action. And if all of you had decided to come in suits and ties and I had come with my Bermuda, that would not have been an optimal action for me. So when we are in a decentralized, in a distributed system with many, many, many nodes who don't know each other and don't interact with each other and maybe don't have symbolics or something like that we heard this morning, it's going to be very hard to coordinate. And when it's going to be very hard to coordinate, we can observe the occurrence of bad things coming up, like bad equilibria, which we heard this morning. We had governance as a way to choose between bad and good equilibria. So what we prove in our paper is that because of these coordination problems, you can have good equilibria and also bad equilibria. So this is joint work with my colleagues from Toulouse, Christophe and Mathieu and Catherine. And I'm so happy we're in Salle Jean Jaurès, because Jean Jaurès in Toulouse, is. So I also like Jean Jaurès for other reasons. But that's not working the way I would like it to work. Okay, I'll do it like that. Okay. All right. So the marketing pitch, people who are doing consultants and they want to sell blockchain ideas, they say, oh, blockchain, it's just automatic. You will get consensus. It's for sure. It's going to be immutable. It's going to be unique. It's the trust machine. Is it? Can we only rely on algorithms to get consensus, or does it take something else? And our point of view is that what's specific about blockchain is that it's not only algorithms, it's human beings making decisions. Okay, so an ideal blockchain would be one in which you have blocks and you have transactions, and the transactions are used to create the next block, and everybody agrees on that, and it goes on and on. However, some things could happen that would not conform to that ideal object, ideal goal. So one first problem that we can see, and that we have seen in blockchains, are forks, in which some transactions will go in one branch, and other transactions will go in another branch. And now we have two different branches, and the question is, okay, where are we going to go? So one way we could go is we are going to abandon one of the branches and go to the next, go to the other one. In that case, the branch we abandon is the orphan. Or another thing that can happen is some people will go on branch A and others will go on branch B. And those branches will continue in parallel. And of course, all this is terribly wrong. Because what we want, blockchain is a ledger. We want to have one ledger that everybody agrees with. We don't want to have uncertainty about what's the right ledger. We don't want to have uncertainty about how the ledger will evolve in the future. Is it going to split or not? And also, we want to avoid wasting the resources that have been used to mine blocks that are orphans. By the way, I should say that my talk is about proof of work, not about proof of stake. And I think one of the reasons is that proof of stake for the moment is not really used yet. But hopefully in the future we'll provide solutions, but for the moment. Okay, so our approach is to say, okay, we want to know if we're going to have one nice consensus or forks. And our approach is to say, okay, who's going to decide that? It's the miners. Because the miners are the ones who choose where to chain their blocks. They are the ones, we talked about governance this morning. We talked about voting. In a sense, the miners are the ones who vote on which branch should survive. And so to analyze the actions of the miners, we think of the blockchain as a game, and we look at the equilibrium strategies of the miners in that game. Now, when you want to do game theory, you need to have the rules of the game, you need to have the beliefs of the players, and you need to have the preferences of the players. What do they get from playing the game? And so the miners, one important thing they get from playing that game in the proof of work protocol is they get rewards. You know, in Bitcoin, if you solve a block, you get 12.5 Bitcoins. Now, something very important, very, very important we have to bear in mind is that those Bitcoins that are the 12.5 Bitcoins that you get when you solve the block, they are written down in your block. Okay? So now, they're going to be valuable to you only if your block becomes the consensus. If you solve a block, you get 12.5 Bitcoins in that block, and then your block becomes orphaned. Your Bitcoins are worth nothing. You spent all this electricity for nothing. So what that implies is that when I'm a miner and I have to decide where in the chain to mine, I want to mine in the branch which I think will be the consensus. Because that's the branch in which my Bitcoins will be valuable. Now, which branch is going to be the consensus? It's the branch that the other miners are going to chain their blocks to. So what I want to do is to chain my blocks to the chain I expect the others will chain their blocks too. And you see clearly this is a coordination game. I want to wear a Bermuda if I anticipate you're going to wear a Bermuda. But if I anticipate you're going to be wearing suits and ties, being alone is very scary. So blockchains, the idea, no central authority, distributed, decentralized. What we say is, okay, great, you need to coordinate. Nakamoto, quite a genius, had anticipated that, of course, and he had suggested a way to coordinate. He said, well, if you don't know what to do, follow the longest chain rule. This is, it's just a suggestion. There is nothing in the code that forces you to do that. All right? So what we show is that, yes, if everybody listens to Nakamoto and follows the suggestion of Nakamoto and coordinate on the longest chain rule, well, everybody anticipates Bermuda, everybody does Bermuda. If everybody anticipates longest chain rule, everybody does longest chain rule. And then the longest chain rule becomes a Nash equilibrium. The problem is, it's not the unique equilibrium. Bermuda is not the unique equilibrium. There's also an equilibrium in which we all anticipate everybody's going to wear a suit and a tie. So there are many, many other equilibria in this game than the long chain rule equilibrium. Okay, so that's... You know, there are two kind of people in life, those who use Macintosh and the others. And I, of course, I belong to the others because I'm not good enough in computers. So. Okay. All right. So let me try to show you in 5 minutes, just to give you a flavor, how we model that game. So we have players, M players, and we start from an initial state of the ledger. The players are rational. They have rational expectations. We're in Nash equilibrium. They're risk neutral for simplicity. And what is the action space? We take a very simple approach. We neglect a lot of important problems. We just say the only thing you have to do is to decide where to chain your block. Now, the nice thing about the blockchain is that the probabilistic structure is very simple. So you know these miners, they are drawing solutions. It's a bit like drawing from an urn with replacement until they find a solution. So in this context, you can describe the stochastic process of the arrival of solutions to the mining problem as a Poisson process. So the probability that you find your solution between time t and just 1 second after time t is a constant parameter that depends on how much electricity and computers you're using. And that thing, something very important for the strategic interaction in the blockchain, that thing does not change with time. It does not depend on how long you tried. It does not depend on what's in the block. It doesn't depend on what the others do. So that's something that is not really like the real world. It's something we did to simplify the model. We said, okay, these guys, they are looking at a certain maturity, exogenous, stochastic, Poisson process, at which they exit the game and they sell their holdings. I'm just telling you about the technique so that you have a flavor of how it works. That's the important bit. When you solve a block, you get a reward. And that reward, the assumption we make, so that reward is in a branch. And the assumption we make is that the value of that reward depends on how many people are active in that branch. So if it's an orphan branch, no one is mining there anymore, the value of your reward is 0. If it's a consensus branch, all the others, all the m-1 other miners are mining there. This is the maximum value you can get for your reward. And in between the two, it's increasing in a number of miners participating in that chain. Okay, so that's a bit boring. It's just we are looking at Markov perfect equilibria in which actions depend only on the state of the system at point t. So that's the maximum you can get in that game. The maximum gain you can get is the term in bracket is the number of times you find a block from now to the point you exit the market because you're hit by the liquidity shock. And as I told you, this is this Poisson process generated thing. And again, we want to bear in mind, it's very important to understand the strategies in that game. That thing is exogenous. It only depends on how much electricity you're using and how many computers you're using. Does not depend on what blocks you mine, what the others do. So the maximum gain you can get in that game is terms in square bracket, which is the number of solved blocks, times G of M, which is the maximum reward per block you can get, because that's the reward you get when everybody is mining in the same chain as you. So you're enjoying the benefit of consensus. So that, immediately, that gives us the first result we have is that mining following the longest chain rule is a Markov perfect Nash equilibrium. Why? Because if I anticipate all the others to follow that strategy, then if I follow that strategy, I get my upper bound, the one we saw in the previous slide. I cannot get better than that, so it's optimal to also follow the strategy. Now the problem is, again, this is not the only equilibrium. We were living happily in the Bermuda equilibrium, in which everybody was wearing a Bermuda, and suddenly we hear that everybody's going to come with a tie and a suit. When we panic and we stop wearing the Bermuda. The same can happen in a blockchain. Let's say you're on Ether, and there has been a hack on the DAO, and we suddenly hear that everybody should rewrite history and come back in past. Well, if we all anticipate that this is what the others are going to do, we do it. And of course, here in the case of the DAO and Ether, there was kind of a good reason. But even if there was no good reason, if we all anticipate that something is going to happen, that the others are going to do something, we're going to do the same. Even if this generates an equilibrium outcome that is Pareto dominated compared to the longest chain equilibrium. We can get bad equilibria. So, to illustrate this notion of equilibrium multiplicity, think about the case of upgrades, maybe SegWit or something like that. So we announced we're going to have an upgrade next week. Now, should I follow the upgrade? To follow the upgrade, that means I'm going to chain my blocks, I'm going to accept the upgrade, and chain my blocks to the branch that accepts the upgrade. Should I do that? Well, if I anticipate all the others chain their block to that chain, I do the same. If I anticipate no one is going to do that, I don't do it. And that's why, maybe you remember what all the discussions before SegWit, there was a November deadline for the implementation of SegWit, and everybody was like asking themselves, are we going to do it? Are we not going to do it? This is precisely the kind of indeterminacy you get in a coordination game with multiple equilibria. The players don't know what they should do, because what they should do depends on what the others are going to do. I try to make it short. It's frustrating, because I'm giving you just, but never mind. So the conclusion is, blockchains are coordination games. So basically, the idea is, blockchain is a wonderful technology because it enables decentralization. Well, what we say is, once you have decentralization, the problem is you get a coordination problem. And in this context, if you coordinate well, you're going to get a good equilibrium, which is the longest chain rule. But if you fail to coordinate well, you can get bad equilibria. And I think it's quite related to the discussions before in terms of governance, Because really, in a sense, maybe governance is about, okay, when we have a bad equilibrium, how do we make sure we get a better equilibrium?
Does it work? Yeah.
Thank you for your speech. In fact, you spoke a lot about anticipation in your speech, and I wonder, based on which information do you think miners are going to make such anticipations?
Yes. That's a very good question. You know what? I got no clue. And in a sense, I got no clue because I'm in this. I have even less information than the players in the game, and themselves. For themselves, it's very hard to know. Think about all the uncertainty there was when we were approaching the November deadline for SegWit. All the developers and the miners, what they were discussing, they were exchanging in forums. They said, we're going to go for it, we're not going to go for it. That's how they try to build their anticipations. And it was hard for them, but it's a lot harder for me.
I'd like to jump into the way you might decide which change to implement. If you keep in mind that miners wants to just at least, good hypothesis, increase the value of their holdings, they will try to follow the chain or the rule that will provide more value, which can mean, of course, better usability. So if you have an upgrade that will bring better usability, that might also be interested to follow this change of rule. And the debate can be very intense on the advantage of implementing something with the compared to the drawbacks of implementing the other thing. And even technically speaking, it might be very hard for them to decide if they have a good argument for this choice or this choice. But when, for example, exchanges that are listing the token publicly state that they will, specifically for Bitcoin, call Bitcoin this token and not this one, or follow the rule, or follow this one, or state that they won't list or will list. That's a very important signal for them to make their choice, for example.
Yes. Oh, sorry. It's easier. Traveling salesman problem.
Yeah, hello. So when you are speaking about the Nash equilibrium that all, for example, the LCR, that all should follow the longest chain because it's, when they anticipate the others are going to do is the best choice for them, you are considering all of the miners have the same hash power, right?
No.
So for example, if one miner...
in the model I showed you, see that you had this Poisson process which has a parameter and there was a subscript. So it's theta subscript small m. So it's completely arbitrary. You can choose any values for the thetas that you want. And the equilibrium does not depend on that.
Okay.
Hello, thank you. I would argue that we can see the blockchain as not being something decentralized. It means that there is only one history, and everyone has to agree on a unique history, which is kind of logically centralized, even if it's physically decentralized by many miners. But yes, I wouldn't call blockchain a decentralization technology.
So in terms of how many histories we have, the way I think about a history is a fork, you can think of a fork as a situation in which there are two competing ways of telling about history. So if you think of the ETH versus ETH classic, some guys said, oh, the history is what happened, and we will never change that. Another guy said, oh, the history, well, we have to change history and, you know, suppress the litigious traits. So that's an example in which you really have two histories. And these continue to exist.
Yeah, of course I don't agree. So that
Who are you working for? I'm joking.
I'm working for a company called Consensus System. So we believe in reaching consensus on something. That's what blockchain are used for. You reach consensus on the state of a ledger, the state of a database, if you want. And that's so blockchain are useful to have large-scale coordination. And the coordination can be more or less decentralized if you compare the different algorithms they are using. For example, proof of authority, you have authorities, they choose where to go. As long as they are choosing to go in the same direction, there is no problem, everybody follow the same authorities. For me, decentralization in the blockchain is more about how difficult it is to be a validator. Is it feasible to be a validator now? Is it cumbersome in terms of hardware to manage? Is it cumbersome in terms of technical requirement to understand how it works? So as long as the being a validator is a very easy process and open for everyone, then we have decentralized governance. And on what we agree on as the state of a ledger, keeps a lot of scars, a lot of events written in it, even if we choose different paths. So technically speaking, the DAO fork was not a reroll. We don't say like, oh, we are at block n plus 10, and we need to go back to block n and rewrite the history. We said like, okay, a problem happened at block n. We are now at block n plus 1000. Let's say that we write a special transition at the next block that will say that right now, at this moment, starting now, that was written here is now that. We just changed history. We changed the page, but we make an addendum saying, if you are reading this, forget about that, take that instead. Which the history itself didn't disappear. The way it should have behaved if the history hadn't changed, well, that's not applicable anymore. That's the incompatible state transition that we do when we hard fork an Ethereum. And yeah, so we still keep the pace of the choices we made. And moreover, since we have a large difficulty readjustment, like if the chain splits, people can keep on mining on a specific chain and perhaps it will still live if it doesn't get attacked. This is how a chain like ETC is surviving, even if it has only a very small portion of hashing power compared to the main chain. It still survives, and it has been able to survive because the block time readjusts very fast, which is not the case on some other blockchain where if you are on the minority chain, you're just stuck and you need to change manually the difficulty to be able to keep on mining. So we can design protocols that are really opt-in, opt-out, and I think it's a good way of qualifying blockchain as decentralized.
I think we're going to close that session. Thank you very much, all speakers. We get a little break, and then we are back again to work in 10 minutes.